Hey everyone, and welcome. Today we're tackling Leetcode problem 474, ones and zeros. This is a medium-level problem that looks a bit tricky at first, but it's a fantastic example of a classic computer science concept. We're going to break it down step by step. Alright, let's look at the problem statement. We're given a list of binary strings, so strings made up of only zeros and ones. We're also given two numbers, m and n. So what's our main objective here? We want to pick as many strings as possible from the input list. It's all about maximizing the size of our chosen group of strings. But, of course, there are some rules we have to follow. And here are those rules. Think of m and n as our budgets. We have a budget of m zeros and n ones. When we pick strings to add to our subset, we have to spend our zeros and ones. The total number of zeros from all the strings we pick can't go over m, and the total number of ones can't go over n. Let's walk through the first example. To make this concrete, we have 5 zeros and 3 ones to spend. Let's see if we can pick the string 1 0. That costs us 1 0 and 1 1. Our budget is now 4 zeros and 2 ones. Cool. How about 0 0 0 1? That costs 3 zeros and 1 1. We can afford that. Our budget drops to 1 0 and 1 1. Let's keep going. 1. Okay, that costs 1 1. Our budget is now 1 0 and 0 ones. Finally, can we take 0? Yep, that costs 1 0. Now we're out of budget. We managed to form a subset of size 4. Notice we couldn't take that long string, because it would have cost 4 ones, which we never had enough of. So the core of the problem is this simple choice for every single string. Do we take it or do we leave it? We could try to generate every single possible subset, check if it's valid, and keep track of the biggest one. But with up to 600 strings, the number of subsets is 2 to the power of 600, which is an impossibly large number. There has to be a more clever way. This problem is actually a famous one in disguise. It's called the 0-1 knapsack problem. Imagine you're a hiker packing a backpack. Each item has a weight and a value. You want to maximize the total value without exceeding your backpack's weight limit. Here, our items are the strings. The value of every string is just 1, because we want to maximize the number of strings. The twist is that our backpack has two weight limits, a limit on zeros and a limit on ones. The standard way to solve knapsack problems is with dynamic programming. We'll build a table, or a grid, to store the answers to smaller subproblems. Let's call our table dp. A cell in this table, let's say dp at I and j, will hold a very specific piece of information. What is the maximum number of strings we can pick if we only have a budget of I zeros and j ones? If we can fill out this whole table, the final answer will just be the value in the cell for our full budget, dp at m and n. So here's the logic. We go through our list of strings one by one. For each string, let's say it costs z zeros and o ones. We then sweep through our entire dp table. For each possible budget of I zeros and j ones, we update our answer. We say, okay, with this budget, what's better? Is it better to stick with the answer we already found before considering this new string? Or, is it better to include this new string? If we include it, our new subset size will be 1, plus whatever the best subset was for the remaining budget, which is the budget, I minus z, and j minus o. We just take the bigger of those two options and update the table. Okay, we've covered the theory and the logic behind the dynamic programming approach. Now let's see how this translates into actual Python code. I'll put the full solution up first, and then we'll break down the most important parts. Alright, here's the full Python solution. It might look a little dense with those nested loops, but it follows our logic exactly. Let's zoom in on the key sections. First, we set up our dp table. It's a two-dimensional grid of size m plus 1 by n plus 1, and we initialize every cell to 0. This makes sense, because with any budget, the smallest subset you can form is size 0. Then, just to be efficient, we loop through the input strings once to count the zeros and ones in each. We store these counts so we don't have to recalculate them over and over. This is the heart of the algorithm. We loop through each string's 0 and 1 counts. Now notice the inner loops for I and j, they count downwards. This is super important. It ensures that when we calculate the value for dp at I and j based on a previous cell, that previous cell's value comes from the state before we considered the current string. If we looped forwards, we might accidentally use the same string multiple times to form one subset. The line inside is exactly what we discussed. The new value for a cell is the maximum of what it was before. or 1 plus the value from the cell representing the remaining budget. So how efficient is this? The time complexity is determined by our 3 nested loops. We loop through every string, and for each string we loop through the m by n grid. So the time is on the order of the number of strings, times m times n. The space complexity is simply the size of our DP table, which is on the order of m times n. Just a quick heads up. We've been walking through the solution using Python, but don't worry if that's not your main language. The logic is exactly the same everywhere. I'll be showing the full code for Java, C++, and JavaScript towards the end of the video. Alright, as promised, here is the full solution in Java. You can see it's structured almost identically to the Python version. Initialize the DP array, loop through the strings, and then run the 2 inner loops backwards to update the table. You can pause the video here to take a closer look at the implementation. Next up, here is the C++ version of the solution. Again, it follows the same dynamic programming pattern. We use a vector of vectors for our DP table, and the logic within the loops remains the same. Feel free to pause and review the code. And finally, here is the solution in JavaScript. We initialize a 2-dimensional array for our DP table, and then apply the exact same nested loop logic. Hopefully, seeing it in a few different languages helps solidify the concepts. So let's wrap it up. The biggest takeaway here is learning to spot familiar patterns. This problem might not scream Knapsack at first, but once you see the structure of making choices with limited resources, it fits perfectly. This shows that the Knapsack idea can be extended to multiple dimensions, in this case, a budget for zeros and a budget for ones. It's a great reminder of how powerful dynamic programming can be for solving these kinds of optimization problems. Alright, before we finish up, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads, and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now, down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.